maximum y value is 228. So a couple of key things to identify here, to notice, are we supposed to just know these values? The maximum, the domain, the range? No, what are we going to look at to get each of these features? Graph it, right?
So, was that the maximum for the, you said it,
Hold on one second, we'll talk about it. So graph the function to get each feature, right? I'm not expecting you to know these features off the top of your head. When it comes to anything higher than quadratic, you're just going to graph the function to get each feature, okay? Now, Gracie has a very valid question here.
I got it now.
But I want you to think about it, because everyone told me this originally. They said the maximum continues up, doesn't it? Yes? Technically, that continues forever to infinity. Well, but is that possible for this box? No. And that's where the context matters, right? The context, my domain is only 0 to 6. My volume, the y, is only from 0 to 228. And so we know how to get that maximum up here. Now, please pay attention to how I'm going to write this. The maximum volume is 228. Notice how the maximum, and you do this for min as well, is the y value. You always write it like that. The max or the min is that y value. It is this number, but then you identify the domain value for it. When the h is what? What was the x value for that maximum volume?
How is it maximum and minimum is the one? Or is it?
Well, so like here we would have a minimum.
Mm.
I'm saying if it's a max or it's a min,
okay.
we would write it this way. In this case, it's a maximum. But if you have a minimum, you would write it this way as well. So when the h is what? What was the h value to get this maximum up here? 2.35. I thought it was 2.35 inches. By the way, context does help. 220 cubic inches. Okay, so notice it is always the y value. The maximum or minimum is the y value when at some domain value x. Right, so we want to break that down and understand how we're going to write that maximum volume.
What does that mean?
In minimum.
So,
So like we have to identify, because I'm just saying the maximum or minimum is that y value at this domain or x value. I don't know what it is, that's why I say some domain value. I don't know what it's going to be each time. In this case, it was 2.35 inches. Okay? Any questions about that? Okay. I'm going to skip the part about x-intercepts. I saw most of us get the x-intercepts. I trust that you can if you didn't, but I want to focus on this. And this is an important distinction. Actually, do I need to wait a second to erase anything? We got the maximum, minimum stuff. I'm trusting my domain and range, which is why I already erased it. Okay, so looking at the next page, I need you to highlight and note this very clearly. Please note, right, is that actually the highest volume on f of x? Not on the volume, but like, is that the highest y value? No, because it can continue all the way up to what? Positive infinity, right? So notice we call it a relative maximum. Is the highest point in a particular section of a graph. Notice if I isolate this section just like you do on the calculator, what's the highest point? That one right there. That's my relative maximum, right? It is the highest point for that small section of a graph. We're going to talk more about what that means when we start talking about increasing and decreasing, but it is important to notice that right there. The other thing is, we can have a relative minimum, the lowest point of that graph, right here. Notice, one, that's not possible in the context of this problem, but two, is that the lowest volume or the lowest y value for f of x? No, because what does it go down to? Negative infinity. So it's not that it's an absolute maximum or minimum, we'll talk about that later, but it is relative. It is the highest y value or the lowest y value for that particular section. You need to know this idea of relative max and min well, which is why it's also on the graphic organizer. You should be able to easily find information about it. Any questions before I continue? Alright, that is all we're doing out of lesson 3. We're going to quickly move a little bit into lesson 4 here. Please notice, what do you think lesson 4 is all about? You just need to go forward a couple of pages in your textbook. Zeros, right? Or what else would we call those zeros? Roots. Or if they're real numbers, they are x-intercepts. Notice how I indicate if they are real numbers, because can we have complex roots? Yes. Yes. Right? Remember how we got those imaginary roots? And can you see imaginary roots on the x-axis? Nope. Okay. So here is what we're looking at. Look at the getting started. This should be very quick and easy. A difference in degree. So we haven't actually named this before, but if you look at these instructions, it says, you know that another name for a linear function that is not a constant is a polynomial. We're going to talk more about this term of polynomial, but it then says degree 1 because the greatest exponent in a linear function equation is 1. Notice right here, what is the highest power? No, highest power. Power, the exponent, right? So this is a degree 1. What is the highest power here? 1. So we would say that this is degree 1. What do we think it would be for C though? How are you getting degree 2? I only see the power of 1.
There's 2x.
There's 2 x's and they're being what? Multiplied. And what is x times x? X squared. So sometimes it is better or easier to distribute, but notice it's a highest power of 2, so it's a degree 2. And what type of function would we call that? Quadratic, right? A degree 2 is a quadratic. So Jaden, D. What's the degree, do you think? Degree 2? Anybody want to push back on that, or do we agree? We agree? So I want you to notice, if we multiply 2 linear functions, what degree are we getting?
3.
Say again?
3.
I said if we multiply 2 linear functions, degree 2. So what am I going to get if I multiply 3 linear functions? The cubic, or degree 3. And so then F, how many linear terms am I multiplying? 3, so it's going to be degree 3. Do you think it's possible to get degree 4? Maybe. How many linear terms would I be multiplying? 4, right? Okay. So that's important to notice there. Now, I will point out, does this include any imaginary numbers? Nope. Is it possible to get imaginary? Yes. I will point out, if I have x squared plus 1, that actually has complex roots. I can't, well, right now I can't factor any further, times x minus 1, what would that degree be? It'd be 3. X squared times x is x cubed. It'd be degree 3. Alright, just a couple minutes to cover a couple of things, but I want us to notice here in number 2, it's the same exact problems, but now we're talking about the zeros of a function, or the points on the graph of the function where the function's value is 0, right? Or if it's a real 0, it's what? What is it also called? It's intersecting the what? X-axis, so it's also called an x-intercept, right? So here is something I want you to notice, and we talked briefly about this before, is the term multiplicity. Is how many times a particular number is a 0 for a given function. So what is the 0 here for a? So 0 is equal to x. Oh, I'm done. What's the 0? X equals 0. What's the multiplicity? Nope. How many times did that 0 show up? that make sense? It's that 1, 0 of x equals 0. Let me show a contrast to that with D. Now 0 is equal to x minus 1 times x minus 1. So x minus 1 is equal to 0. So what does x equal?
1.
X equals 1, right? But how many times did that 0 show up? Say again? That's what it gives us in D. I'm not looking at B, sorry, I jumped to show you multiplicity. See how that showed up twice? So we would say that's a multiplicity of 2. So every time that factor, notice how the factor is associated with the 0, every time that factor shows up, it increases the multiplicity. Right? So you have to find the 0 that goes with that factor, and then we identify the multiplicity. We'll pick back up with that tomorrow. Hopefully move through it somewhat quickly. Alright, in closing. Alright. You have homework that is due on Friday. It is not a lot. But I would go ahead and knock it out because, and you can already go ahead and I think do all of this homework. We will start Literacy for All on Wednesday, and whatever you do not finish on Wednesday, you'll have to do for homework on Thursday since we don't have school on Thursday. Right? It's Veterans Day. I will also be giving you, I already have it. Just the right portion of M1-165. There's actually one thing I'm missing from this, and I think it's on the next slide. Hold on. You have over a week to work on this, but I do want you to notice also on Tuesday the 16th, that review I gave you for the quadratics unit, I'm asking you to do some work with it. I'm asking you to do some extra work with the quadratics unit. I will give you all a paper for this tomorrow. You remember when we had that review packet? It's like 45 pages to prepare for the quadratics test. There are, look, do those problems by next Tuesday. But you have a little over a week. I just want to go ahead and give you a heads up. Yeah.
Is your thing still recording?
Yeah, I know.
Okay.
I just never paused it because we kept stopping and coming back to the board pretty quickly, so I just never paused it.